Today we will be talking about the Zeeman effect. But first, to talk about the Zeeman effect, we have to talk about an atom. An atom has protons, positively charged particles, and neutrons, neutrally charged particles in the nucleus, and negatively charged particles orbiting the nucleus. Here is an electron, a negatively charged particle, and it rotates around the nucleus of the atom. Now, as the electron rotates around the nucleus of an atom, it creates an effect called a magnetic dipole moment. And this is caused by the spinning of the electron around an atom. Now, as the electron rotates around the atom, as I said before, it causes a magnetic dipole moment. And that is referred to by the Greek letter mu. Now imagine this as an actual magnet with two poles, a north pole and a south pole. And this is analogous to a magnetic dipole moment created by the spinning of an atom, where the atom is separated into an upper pole and a lower pole, which have different magnetic dipole moments. And that is perpendicular to the area of the spinning of the electron, as shown. Now, magnetic dipole moment can be affected by a magnetic field. When a magnetic field is applied to the atom, I will place the atom right here with the electron spinning, magnetic dipole moment, and I will apply a magnetic field to it and designate that as B. Now, the magnetic dipole moment will experience a torque and will align itself to the magnetic field. So they are parallel with each other. So a torque will be applied and it will eventually align itself with the magnetic field. Now, the Zeeman effect involves the splitting of spectral lines into two or more emission lines by a magnetic field, by the splitting of p orbitals. Now, we must talk about orbitals of an atom. We won't get into too much detail because that is not necessary for this topic, but the basics of the orbitals are: an atom is right here, and an s orbital is just a spherical orbital around the atom, the most basic form of orbital, just an electron moving round and round around the atom. But we are concerned about p orbitals, which are higher energy orbitals, which you find with molecules with more electrons. And the p orbitals are shaped as such. And now you can find these p orbitals on each axis of the atom. On the y-axis, the x-axis, and also the z-axis. Maybe I can show a better picture. Y-axis, x-axis, and a z-axis going into the board. And these p orbitals are each aligned with these axes. Now, as I said before, that the spinning of an electron creates a dipole moment. Each p orbital in the y, x, and z axes of the atom each has its unique dipole moment. And when placed in a magnetic field, each of these magnetic dipole moments of the p orbitals will align themselves to the magnetic field. So I will place another magnetic field as such, magnetic field B, and all these p orbitals will align themselves. And now, because of the orientation of the p orbitals of the y, x, and z axes, some of these orbitals have to rotate more to align themselves to the magnetic field than others. For example, the y-axis has to rotate 30 degrees, where the x-axis has to rotate 60 degrees, and the z has to rotate 90 degrees, for example. And now the torque applied to these p orbitals increases its overall energy. Now, on an energy graph, energy and the orbitals, all three of the p orbitals share the same energy level. But when a magnetic field is applied, the torque applied by the magnetic field changes the energies of the three p orbitals, splitting the energy levels into 3 or more energy levels. 1, 2, and 3. Now this is the Zeeman effect, which is the splitting of spectral lines into 2 or more emission lines by a magnetic field, or the splitting of p orbitals. Now, to recap, one spectral line is continuous until it reaches a magnetic field. Now, the magnetic field will split the spectral lines into multiple emission lines depending on the strength of the magnetic field. So a larger magnetic field will split the spectral lines into more emission lines, and that is proportional to the strength of the magnetic field. And that is the Zeeman effect. And I hope you could learn more about the Zeeman effect, and I hope you enjoyed this video. Thank you and good night.